All right, let's continue. In the first circuit we look at for op amps in this lecture is the inverting amplifier. Okay, inverting amplifier. So this is a typical circuit of a inverting amplifier. You and as I stated earlier, we typically draw with the inverting terminal at the top and the non-inverting at the bottom, or non-inverting below. If we are giving the input signal at one of the terminals, typically the other terminal will be connected to ground. Okay, so here the input is being driven into the inverting terminal, and when it goes into the inverting terminal, when we connect it to the inverting terminal, the non-inverting terminal is connected directly to ground. So what happens? We have so ignore the load resistor for now. We don't really care about that for now. We have negative feedback provided by R2. So negative feedback provided by R2. Because it is in the feedback path, sometimes this resistor is also referred to as RF. RF. Okay, so if you maybe go to a different website, use a different book, use a different lecture notes, this will often be referred to as RF. The F is for feedback. And the resistor R1 is in the input path, and so sometimes it is also known as RI, the input resistance or the input resistor RI. Okay. So now, what happens? Let's see. We have I minus going in here. We have I plus going into the positive terminal. The difference between the two voltages is Vx. Because this is connected directly to ground, we can say this is 0 volts. Also, the property of the op amp is such that the input impedance is very high. No current is flowing between the two terminals. Voltage across them is equal to 0. So we sometimes also refer to this point as connected to ground. Virtual ground. Right? Virtual ground. V plus is connected to ground. And V minus can also be stated as connected to ground. Virtual ground. Okay. Now, Vx is V1 minus V2, or we can say zero volts. In reality, there is some differential voltage and some differential current that actually goes into the op amp. Obviously, an ideal op amp, nothing will go in, but real life, something is going in. Okay. Two other points I think I should have mentioned before is that the op amp is powered by supply rails. So let's talk about those. In the first slide, I drew out plus VCC and minus VEE, supply rails. The ground connection or the negative terminals of both supplies may or may not be connected together, does not really matter. But on the actual op amp symbol, it is shown like this. There are two power supply rails, plus VCC at the top, minus VE at the bottom. Most of the times when we analyze circuits, we don't even draw it out or we don't even mention it. It is simply assumed or understood that there is power supply being applied to that circuit from somewhere. Okay. That power supply is being applied to that circuit. So plus VCC minus VEE is simply implied. In this diagram too, you can see. So even though the diagram does not have it, it's here and here. And this power supply value is what limits the output voltage, right? You have a transistor. The transistor is being applied 10 volts. Then your output saturates at 10 volts. It cannot go beyond 10 volts. Doesn't matter what kind of input signal you give. Your op-amp could have a gain of 100,000, but if the voltage you're applying is plus 10 volts, the maximum output you'd get from there is plus 10. Cannot get more than that. Energy has to come from somewhere. For all circuits, the energy comes from our biasing voltages, the supply voltages, okay, plus V and minus V. Anyway, so if we have this, how do we analyze? Two ways to begin analysis. KVL, KCL, that's it. KVL or KCL. In most of the transistor circuits, the load line analysis, we were dealing with voltages, so we applied KVL. Remember, on the input side, on the load line, we'd apply KVL, write out our equations because we wanted answers in voltages. And the output side, again, we would apply KVL. So here, we can apply KVL. People have done that. But obviously, since they have done it, we know that a better solution would be to apply KCL. So we will apply KCL, and then from those equations, we will determine the output voltage V out. Okay. So again, analysis, first step is to check if you have negative feedback. Yes, we do have negative feedback. Check V in, check I in. We check V in is Vx, which is equal to 0. For the purposes of our analysis, we are assuming that the inverting terminal is at virtual ground. And if it's at virtual ground, then the difference between the two is 0 volts, which is Vx is 0 volts. So total V in is being driven to 0. If you apply KCL at the input, we want to say, and we'll take the reference directions for the currents as this. We have I1 going in. And because, you know what, let me draw it up this way. Because we are saying that I minus is equal to 0, where is I1 going? What other pathway can I1 take? You have three pathways, right? You have 1, you have 2, and you have 3. So if you apply KCL at that node at the inverting terminal, what do we see? Yep, it goes into the feedback resistance. So note, the inverting terminal node has 3 connections. One is connected to the incoming signal. The second one is going into the op-amp, and the third one is the feedback resistor. If our assumption is that the input going into the terminal, I minus is equal to 0, then the only conclusion, the only logical conclusion we can take from KCL is that I1 is going through the feedback resistance. So let's give a name to that current. And because the current's going to go this way, I'm going to give it a direction like this, I2. Okay. So if I apply KCL, at the inverting input, I would obtain I1 is equal to I minus plus I2. And because I minus is equal to 0, I can write I1 is equal to I2. Again, when you first begin analysis, this was an assumption on our part. Op-amp has infinite input impedance, so we say the current is not going into the terminal, so we are making an assumption. And that's how all of these numerical methods work. You make an assumption, you analyze the circuit, you verify your answer. Does it make sense? If it does not, you go back to the beginning, you make a different assumption, use a different model, and then you analyze the circuit again. Okay. So in this case, right now, in the classroom, we are presenting this as simply because we know it. Lots of people that came before us decades ago already performed these analyses, but they did not arrive at that solution in one step or in one shot. Okay. Let's take a pause, think over all of that. Let me know if you have any questions. Yes. Yep, that is correct. So the question being asked was about how and why I minus is 0, and I minus is assumed to be 0 because the op-amp has very high input impedance, or at least an ideal op-amp is said to have infinite input impedance. Nothing is going into that terminal because of that infinite impedance. So all of that current must go through the feedback resistance. And again, theoretical methods on paper or analysis, it's always ideal components. Okay. In real life, a small amount of current is going into the op-amp. Okay, so now node voltage analysis. Remember, express the currents I1 and I2 in terms of the resistor voltages, and then express the resistor voltages in terms of the node voltages at either end of that resistor. I1 is flowing through R1. So we can write, this is VR1 divided by R1, and this is VR2 divided by R2. Ohm's law. Again, repeating the same thing. You only need 3 laws or 3 equations to analyze all circuits. Ohm's law, KCL, KVL, nothing else. So we applied KCL, made logical assumptions. Those assumptions, we won't know whether they're correct or not until the end, right? I1 is equal to I2, Ohm's law, VR1 divided by R1 is equal to VR2 divided by R2. Where is VR1 connected? Sorry, where is R1 connected? R1 is connected to Vin and the inverting terminal. And this is where the second part of that assumption comes into the picture. Non-inverting terminal is connected to ground. So that is 0. Because of the virtual ground assumption or the virtual ground logic, we say the inverting input is also connected to ground. That also has a voltage of 0. And that has a voltage of 0. We can write VR1 as Vin minus 0 divided by R1. Let me write it as V minus, and then instead of skipping on the step, then VR2 is of course V minus, and here the voltage at the output terminal is V out, VO. So the voltage across R2 is VO, and here it's V minus. So this is VO divided by R2, and V minus is 0 from the virtual ground concept. So this becomes V in over R1, and this is minus VO over R2. Rearrange the terms, what do you get? V out over V in is minus R2 over R1. And that is the equation for the voltage gain of a inverting amplifier. So write it down, think over it, let me know if you have any questions. Do the steps make sense? Any questions? Yes. That's from the virtual ground concept. Virtual ground concept. So question being asked is, why is V minus equal to 0? Is because the op amp has infinite input impedance. And because it has infinite input impedance, the current between the two, V in 1 and V in 2, the inverting and the non-inverting terminal, is effectively 0. If it is effectively 0, that means that the voltage at both ends is the same. So we make an assumption where the voltage at the minus and the plus terminals is exactly the same. If we ground one terminal, then we can say the other terminal is also virtually connected to ground. Yes. A is gain. Yeah. V out or V in is always the gain. Yes. So V out or V in is always gain. Or amplification factor, if you will, right? How is the input being transferred to the output? Chapter 6, it's also chapter 6 of 201. It's also known as the transfer function. It tells you how the input is being transferred to the output. So we want to, because it's an amplifier, the function is basically amplification. So we say gain. Okay, so the transfer function of this circuit is gain. And gain is typically referred to as A. Voltage gain is AV, current gain would be AI. Again, the virtual ground concept is a little tricky to understand at first, but again, it comes from the fact that the op amp has infinite input impedance. It's infinite input impedance. We say there is 0 current flowing between VI and V plus. So if V plus is connected to 0, then we say V minus is also connected to 0, virtually, not physically. All right, any other questions? Okay, so this, as I said, is the fundamental expression for a voltage gain of the inverting amplifier. But now let's think about what it actually means. You take an op amp off the shelf, you buy an op amp off the shelf, right? Two components, R2 and R1. You don't have to design anything. You're buying it off the shelf. It's an off-the-shelf component, so it comes with the manufacturer's spec sheet. It tells you, the manufacturer's spec sheet will tell you what frequency range you can use that op amp, what temperature range you can use that op amp, what kind of gain is possible, what kind of frequency limitations that op amp has. If you're just designing a simple amplifier circuit, all you need to do is choose values of R1 and R2. If you want a gain of 10, simply take R1 as 1K, R2 as 10K, done. R2 or R1 is 10. Make sense? The minus sign simply indicates that the output is inverted. That's all it means, okay? The minus sign simply means the output is inverted. So it's referring to the phase of the waveform. If your waveform looks like this, then your output, if this is your input, then your output is going to look like this. 180 degrees out of phase. That is all that negative sign indicates. Again, mathematically, we have to have a plus or minus sign. In this case, it just turns out that it's minus R2 or R1. If you didn't have the minus sign, our equations would never balance out. Any other questions? Yes. Mm-hmm. It is out. Oh, so it just means that whatever input we are giving, it's phase shifted by 180 degrees. So if the incoming signal has a phase of, let's say, 45 degrees, then it would be 180 degrees out of phase. If the input, let's say the input had a positive at, so in this case, on the x-axis, is time. This is V, voltage here. So if your signal looked like this, in terms of time, this is 0. 0 simply means the point at which we begin our analysis. So if the signal reaches a maximum at this point, then the corresponding point for an output will be the lowest peak. A real life example of this is noise cancellation technology. Noise cancellation is present in every phone that was ever, even before phones came into, into the picture. Even the small flip phones that we used, you can take a look right where the speaker is. There's a tiny hole opening. There's a microphone near that speaker that captures the surrounding air, surrounding noise signals, and it captures that signal. You give it into a circuit that looks like this, inverts it 180 degrees, because when you invert it and when you add these together, the result is 0. So noise cancellation technology, this is the fundamental principle of noise cancellation technology. You take an incoming signal, you invert its phase, keep the amplitude and the frequency exactly the same as it is, and you add them together, the output result is 0. And you can mathematically verify this. You can take 1 cos omega t and add 1 cos omega t minus 180 or plus 180 to that signal. Mathematically, the output result would be 0. Okay. So that's the real life example where we would use this. And if we didn't want an inverted output, then we would use, depending on our use case, we would use a non-inverting, which is the next circuit that we'll look at. Or if you didn't want to use the non-inverting, because there are some limitation, positives and advantages to both circuits, we would use a 2-stage amplifier where your first stage would invert it by 180, and then use a second stage, invert it one more time, and then you would get 360 back to 0. Okay, so noise cancellation. If you use a noise cancellation headphone, it is broken down into two. Noise cancellation technology. You have a physical grip around surrounding your ear, whether it's noise canceling earbuds or whether it's noise canceling headphones. Physically, it will prevent as little noise coming in as possible, and then electrically, it captures the surrounding signals, inverts it, and then feeds it back into the circuit, and so it goes to zero. That's why they are not as effective. It only works for certain frequencies. It cannot block out everything. It is designed, noise cancellation technology is designed to block out human hearing, most of it. So if you're in an airplane, it's not designed to block out a lot of the other air signals, that you can encounter in an airplane, high frequency signals or low frequency signals. Okay. Anyway, let's look at a small example. So let's see, where do I want to write this? Let me scroll down. I'll write this on the left side. Okay, so we have, we have an op amp, minus and plus. We have V out, input resistance, feedback resistance. And then in the output, sometimes we just leave the output as V out like this, or we would want to show the output resistance. And we'll say the output resistance is 1 kilo ohm connected to ground. This is V out. V plus is connected to ground, and we're giving in V in at this point. Note that the op amp itself only has power supply rails of plus V and minus V, right? Plus VCC and minus VCC. The op amp circuit itself is not connected to ground. Okay, the inverting and non-inverting terminals, yes, depending on a use case scenario, we would connect those to ground, but the op amp itself is not connected to ground. Okay, and so the important takeaway from there is that the outputs are floating. They are not tethered or connected to ground anywhere, unless we take our output like this and connect it to ground. Okay. All right, so if you wish to analyze this, let's say, for example, V in given to us is 1 volt. Given information, let's say R1, R2, RL, load resistance. V in is 1 volt, R1 is 1 kilo ohm, R2 is 10 kilo ohm, and RL, let's say, is 1 kilo ohm. Okay, 1K, 1K, and 10K. Right off the bat, we know that the gain is minus R2 or R1. So we'd expect our gain to be minus 10K divided by 1K, or minus 10. Okay, minus 10. So if we wish to analyze this, we'll use the same steps. Let's say this is I1. This is I2. And then this is IO. Actually, there's 2 of them. IO. This is still I2. And let's call this, all right, let's call this IX. Okay, Ix. So we have two resistors for the op amp, R1 and R2. Non-inverting terminal is connected to ground. So we can right away see it has negative feedback. It is a inverting amplifier. Inverting amplifier gain is minus R2 over R1. So 10,000 divided by 1,000. So the gain for this circuit is 10. The other parameters given to us is that the input voltage is 1 volt. Then we make assumptions. Current I1 is flowing through R1. Current I2 is flowing through R2. Current IO is flowing through the output resistor RL. The voltage across RL is VO. And it's measured with this polarity, plus minus. And then the output current coming from the op amp is IX. IX. Since V plus is 0, V minus is also 0, virtual ground. And I1 would be equal to I2. Same thing as we analyzed earlier. So let's write V plus is connected to ground, so it's 0. Therefore, V minus is also 0 volts. Now, I1 would be 1 volt. V in minus, V in minus V minus divided by R1. So it is 1 volt minus 0 divided by 1,000 gives me 1 milliamp. 1 milliamp. Same equation that we obtained from the previous circuit. I1 is 1 milliamp. Okay, and because infinite input impedance, I1 is equal to I2. So I2 is equal to I1, which is equal to 1 milliamp. I2 also has a value of 1 milliamp. Now, I2, as previously described, we can write as V minus minus VO divided by 10K or R2. And so it's 0 minus VO divided by 10,000. Because I2 is 1 milliamp, I can write VO is minus 10 volts, which of course is what I already know. Right? We already know this, but this is just the analysis steps. VO would be 10 times V in, which is 10 times 1 volt. Then let me write it on the right side. Actually, let's just do it here. Okay, so if VO is minus 10 volt, I can write IO is minus 10 divided by 1,000, get minus 1 milliamp. Minus 1 milliamp. Oh, sorry, minus 10 milliamps. Minus 10 milliamps. And then lastly, KCL at output node gives me Ix plus I2 is equal to IO. Therefore, Ix is equal to minus 10 minus 1 minus 11 milliamps. Minus 11 milliamps. Let's take a pause while you write it down. Let me know if you have any questions. So the question being asked was about IO. IO is, I can add a step here. This is VO divided by RL. So this is IO. VO divided by RL. So again, this is a simplistic well, not simplistic, but straightforward, simpler example of how you would analyze a amplifier circuit depending on your need. If you wish to see how the output resistance would affect the op amp, we could change the value of the output resistance and see calculate the currents that are flowing in the circuit. If you wish for larger gain, you would change the value of the resistances. In this case, we're not concerned about any other factor except the gain, right? As a larger circuit or as part of a larger circuit, there's always a lot of important considerations that we have to take into account, right? In this case, we are only concerned about the gain. We don't care about what kind of effect the values of the resistors will have on other parts of the circuit. We simply want R2 over R1 to be 10, or we want R2 over R1 to be over 20 or 50 or 100, as the case may be. And that's all we care about. But again, depending on our use case scenario, we would calculate a lot of other parameters. All right. So then let's take that one step further. And what happened here? And use it as a summing amplifier. A summing amplifier. The circuit is exactly the same. You have a feedback from the output going into the negative terminal. So it's negative feedback. Positive terminal is grounded. So V plus is equal to 0. So V minus is also equal to 0. We would say, and this time the notations are F for feedback. We have two inputs connected to the non-inverting terminal. And say it's A and B. A and B. Let's say this is IA. Because it's uppercase, let's stick with uppercase. IA and IB. This is V plus and V minus, and then we have V. Okay. So if we apply KCL at inverting terminal, what do we get? We have IA plus IB entering the terminal. You would say I minus and IF are leaving. So it would be IF plus I minus, but I minus is equal to 0. Therefore, IF is equal to IA plus IB. We do the same steps as we did for the previous one. We express the currents in terms of Ohm's law. So voltage across the resistors divided by the resistors, and then express each resistor voltage in terms of the node voltages. Excuse me. So I can write IF is 0 minus V out or VO divided by the feedback resistor RF. Then IA VA over RA plus VB over RB. And then this would be minus VO over RF is equal to let's take it on the other side. So V out if I say minus RF on this side, VA over RA plus VB over RB. Okay, what do we get? We get that V out is minus RF over RA times VA. And then this would be minus RF divided by RB times VB. If we keep the minus sign outside and we state, or if we assume that RA is equal to RB is equal to, one standard value of R in RI. So let's say if we choose the value of RA to be equal to RB, and we state that value is RI, we can write V out as minus of RF or R in, and this would be VA plus VB. And that's it. We can skip from that step to that step. Any input signal we give or combine as a single node to the inverting terminal or the non-inverting terminal for that matter is summed up. The feedback gain remains the same, minus RF over RI. The reason I did the step in the middle, which is this step right here, is to show that if you wished, we can design the circuit to provide individual gain for each stage or for each input. Okay, we can provide individual gain for each input. We keep the minus sign outside. Let's say I keep the minus sign outside. This just shows it's the negative. And then I have RF over RA and RF over RB. If I wish to amplify two different signals and sum them up, I can choose different values for RA and RB. Does that make sense? Right? So it's 2-in-1 application. You're summing them up, plus you're amplifying. And depending on your chosen application, you can keep them the same values, or you can choose different values. Hence, this works as a summing amplifier. A summing amplifier. The negative sign, of course, is simply that it's an inverted summing amplifier. We can do that same thing for a non-inverting terminal also. Let's take a pause. Let me know if you have any questions, and then I'll cover the non-inverting amplifier. Any questions? Okay. I'm going to speak. I'm going to skip over this for today because I don't have time to cover this in depth. But I want to talk about non-inverting amplifier. We'll do the derivation because it's short. And then this I'll cover on Wednesday. This again is a inverting amplifier, except the feedback path has a few different resistors. Not one single one, okay? All right, so non-inverting. Take 10 seconds and look at the circuit diagram. Okay, what do we see? Just for ease and for clarity, the non-inverting terminal is at the top, inverting is at the bottom. For me, I'm kind of like a creature of habit. So if I was to draw this circuit diagram, I would draw it like this. We have V out. We have V in, negative, positive. And because we are giving the input to the non-inverting terminal, this would be V in here and our feedback resistor. Feedback resistor up here. So this would be RF or R2 in this case. This would be R1. These diagrams are exactly the same, no difference. Okay. Students should just keep that in mind and be used to, the different ways that we can draw circuit diagrams. All right, so this one, again, as I said, straightforward. First, let's check. Is there a negative feedback? Yes, there is. We take the output and you're feeding it back into the input terminal. So negative feedback. Current, again, is II is equal to 0. II is the current going in. And because II is 0, sorry, not II, this is I1 from the negative terminal. This is II at the top. Because again, we have high input impedance, no current is actually going into the amplifier. We state that II, the input current, is equal to 0. I1 also we say is 0 going into the negative terminal. Okay. VI, that is the difference between the two, we also assume to be 0. Okay, VI and II, we assume both of them to be 0. However, in this case, the terminal of the input terminal of the op-amp is not connected to ground. Okay. Positive terminal is connected to V in. Negative terminal is connected to a voltage divider network. R2 and R1 create a voltage divider network. And that is the reason why the circuit diagram is drawn in this way. You have V out connected, V draw it out. This is VO, this is R2, this is R1, and this is the node that is going into the op amp, VI, sorry, not VI, V minus, negative. And because we are using the virtual ground concept, or at least where the concept where both input terminals are connected together and are the same voltage, we can say V plus is the same as V minus. This is the voltage right here that's going in. That is equal to V1. And V1 from here we can see is VO times R1 divided by R1 plus R2, voltage division. VO times R1 over R1 plus R2. So now, since V1 is VO times R1 divided by R1 plus R2, from the concept of the virtual short, same concept that we use for virtual ground, we can say the input at the non-inverting terminal going into the op amp is also the same value. Okay, again, that comes from the fact that the op amp has high input impedance. So we assume the terminals are connected together, virtual ground, virtual short. The voltage levels at both terminals are the same. So the assumption is that VI or V in is the same as V1, which is VO times R1 over R1 plus R2. We rearrange the terms and we can write VO or VI is one plus R2 over R1. No negatives here because it's a non-inverting amplifier. And that is the voltage gain of a non-inverting amplifier. AV is 1 plus R2 over R1. Right? R2 over R1. Let's take a pause. Let me know if you have any questions. Yes. Yes. Assumptions. Those are all assumptions. The entire circuit analysis, again, analytical methods. We have fixed equations. We know that if you apply Ohm's law to a system, it gives us a fixed answer. Electronics, numerical methods. We create a lot of analytical models. We make a lot of assumptions. We try out one of the assumptions, see if the output makes sense. If it doesn't, we go back to the beginning. We make a different assumption, different model, analyze the circuit again, and then it's an iterative process. We keep going until we find an answer that applies to the system and makes sense. Obviously, in this case, I am simply presenting what you already know works. If you were analyzing a different kind of circuit from scratch, we would make an assumption, analyze it, keep repeating the process until we find the final answer. Okay, if there are no more questions, we'll end class here today, and I will see you all on Wednesday. There is homework for the transistor that is, I think, due today or tomorrow, and then there'll be an op-amp homework. So get started on it. Do not wait. If you have any questions, I have a few minutes before my lab class. I'll be happy to answer any questions. For now, we will close Monday's lecture at this point.